Okay, so this work has been done in very close collaboration with Professor Qianshu Zhen, who is focusing on experimental part of the work. And most of the work has been done by students here in Tel Aviv University. And one of the postdoc students in my group, Ming Ma, he has done PhD with Professor Zhen, and he is now doing very interesting work, and I will tell a few words about this. We all have experience with friction, and we all know that friction depends on the weight of the object which you would like to try to move, on the properties of the surface, and probably the first scientific studies of friction have been done by Leonardo da Vinci something like 500 years ago. But even now, I have to say, there are a lot of fundamental questions which we still cannot answer. And what I like in this field, that this field actually involves a lot of fundamental questions, fundamental scientific questions, but also can lead to very important applications. Friction is important at different scales, and I show you here just a few examples. This is nanoscale. There are friction between in the hard disk, between the hard disk and head. Reading information from the hard disk is very important. If you would like to increase the rate of transfer of information, you would like to bring your head as close as possible to the surface, and friction, of course, is limiting this process. At larger scale, friction is important in joints, and unfortunately, I myself have this problem playing tennis, and this is really very, very hot topic in friction. At geophysical scale, here you see result of earthquake. There you have friction between tectonic plates, and this is also friction. Friction is not always obstacle, as Jimmy told you. For instance, we can enjoy music, enjoy violin. Here you see response of different quality violins, and we can enjoy music only because of friction. This is kind of stick-slip motion, and we enjoy music because of this. Now, when we move to smaller and smaller scales, friction becomes more and more important. And the reason is very simple. Just the surface to volume ratio grows dramatically when you go from macro to nanoscale, and now functioning of many machines at microscale and particularly nanoscale critically depends on our possibility to control friction. So we are asking a question, we are trying to find new approaches to control and modify frictional properties at different scales, from nano to macro scale. What are the goals? Usually there are two goals. First of all, in most cases, you would like to decrease frictional forces and in this way to reduce energy dissipation. And also you would like to transform non-uniform, so-called stick-slip motion, where you move, stop, move, to smooth sliding. Okay? And this has a lot of very high technological importance for many, many different devices. This also allows to reduce wear, and I will not talk about applications today. So what are our approaches to control friction? I will start with the approach which is called structural superlubricity. It's very easy to understand the idea. What is the idea? We all know these egg cartoons. If you put them in registry, in so-called commensurate state, it's very difficult to move one surface with respect to another. But if we just rotate a little bit one with respect to another, they are not in registry. This is so-called incommensurate state, and you can move them. Actually, the same idea, very similar idea, is working at the interface between different materials. You can put materials in a registry, you have high friction state, you can take them out of registry, and you can get low friction state, so-called incommensurate state. Very recently, actually, the professor from our School of Chemistry, Odette Ott, suggested very efficient method to define degree of incommensurability, and I hope this will be useful also for studies of friction. Now, what do we know experimentally? Already probably 10 years ago, the people in Leiden have done very beautiful experiment showing that superlubricity really exists at nanoscale. Experiment is very simple. Okay, you have tip of atomic force microscope. You attach to this tip a flake, nanoscale flake, with radius of about 10 nanometers, and you study the friction between this graphite flake and graphite surface. And you see here, you put them in a registry, you have very high forces, non-uniform motion, high friction. You just rotate them a little bit one with respect to another, and you have low friction state. And this was really exciting. You can create low friction state with low energy dissipation. Unfortunately, life is not so simple. And we found, actually both experimentally and theoretically working with this group, that you put these surfaces in this very low friction state, which you like to achieve, but after short time, friction grows, and you come to high friction state. You can look at this like at kind of Le Chatelier principle. Okay? It's very hard to work against nature. So what's the reason for this? Just when you move one flake along the surface, there is a torque which would like to bring these surfaces in commensurate state. Actually, in the case of nanoscale, when the sizes of contact is very small, of the order of few or maybe tens of nanometers, we found a way how to resolve this problem and how to keep low friction state working. Now, why all this is important? Graphite actually is known like an excellent lubricant, working at high temperatures. We add this to liquid lubricants, and actually it works in electromotors. And until now, actually, we do not understand why it's working so well. And because of this, actually, and we know sometimes it works, but it doesn't work under humid conditions. So we do not know what is the situation. There are many ideas, and we think now that probably here also we have kind of super lubricity, because when you put graphite between two surfaces, like in a engine, actually you have graphite flakes between two surfaces, and probably this you have super lubric state. We studied this in simulations, and we found, yes, putting graphite between two surfaces, you can achieve very low friction state. Unfortunately, this state is not always stable, and so far, actually, we do not have complete answer to this question. But real challenge, actually, is to scale up super lubricity. If we will be able, as I told you so far, experimentally we know that this low friction state exists only at nanoscale. And actually all experiments which have been done so far have been done in vacuum. If we would like to bring this super lubric state to real applications, we have to scale up our systems, and we have come from vacuum to gas. Okay? So what are the problems on this way? There are a number of problems. Okay? First, you have to prepare large-scale surfaces which provide you super lubric state. Second, actually, you have to achieve super lubricity at high speeds which are relevant to real applications. We found actually that if you come to larger scales, you have all these samples becomes elastic. Elastic properties of these samples becomes important and can enhance friction. Another very difficult problem, if you would like to do, and actually this is what we would like to do, to apply this in air, for instance. In air, you have adsorbates on surfaces, you have different kind of contaminants, and they can pin surfaces and enhance friction. So this problem we have to overcome, and this is focus of our research, and this is what we are doing, and this is what we are planning to do. Part of these problems have been resolved. For instance, in the laboratory of Yuan-Shizhen, they succeeded to prepare microscale, coming from nanoscale to microscale. This is 3 orders of magnitude. Prepare on microscale surfaces which demonstrate super lubricity. Low friction state. We studied this system together, and we found actually that in these systems you can achieve very high velocities which are already relevant to real applications, and you can do these measurements in vacuum in wide range of temperatures. Now, very recently, we started to think what are the limits of this super lubricity. As I told you, at larger scales, elasticity of the objects plays important role. And here, Ming Ma, who came to my group from group of Professor Zhen, has done very beautiful research. And actually he found that up to some length scale, you can get very low friction state. But suddenly, when you increase the scale, you have jump in energy dissipation. It comes like phase transition, okay? You have jump, and you cannot do. You cannot go to longer distance. You will create ideal surfaces without adsorbents, without contaminants, but your friction will be high. This is effect of elasticity. Now we know how this critical length depends on properties of materials, on physical conditions which you use for your measurements and for your applications, on driving velocities. Another problem which we have to overcome if we do measurements, experiments, and applications in air, in real air, you have to somehow to clean your surface. And it was found also in experimental works done in the laboratory of Q and Shuzhen that actually when you put one graphite surface on another graphite surface at small scale, you can clean surface. You have kind of nanoscale eraser, okay? Just, moving one surface with respect to another, performing this oscillatory motion, you take out contaminants from the area of contact. Now we are trying to understand what is the origin of this phenomena. And in our simulations, this already started to work. Okay, I will probably show you just, okay, if this movie works. So here you see actually how this nano eraser works. You have some molecules in between. This is results of simulations. And you see how the amount of these molecules in between decreases. And basically we are studying this phenomena now. And we are trying to understand under what conditions it's working and what velocities, what loads we have to apply to perform this, to create this nanoscale eraser. Okay, will it move or not? Okay. Okay, now this was one of our approaches to modify friction. Now we are working also on another approach which I will call dynamic superlubricity. What is the idea of this approach? The idea is, in this case, we are not trying to modify properties of the surfaces. You give me surfaces, they have high friction, and not always you have a room to put between two surfaces lubricants. So what is the idea? The idea is to apply very tiny oscillations, very tiny vibrations to the surface. It could be in normal direction, it could be in lateral direction, and in this way to try to influence friction. Actually, we started with this work with the president of our university, Yossi Klafter, many, many years ago, let's say, when our office was just one near another, and it worked on computer very nicely. You have high friction, you apply very tiny oscillations in normal direction, and you get to low friction state. And when we suggested this, it was extremely difficult to publish these results. Everybody told us, you are completely crazy. This is so complicated system. This will never work. Okay, we succeeded to publish this, but unfortunately at that time we were naive. Actually, we did not apply for a patent. So very soon after that, people started to do measurements, and I show you just one of these measurements where people applied very tiny oscillations and came to very low friction force. And I will tell you even more. Now, for instance, IBM, they developed storage device, based on this idea. This is called millipede. Okay, so applying very tiny oscillations, they increased 4 orders of magnitude lifetime of device because of very high friction. Actually, you try to write something and you destroy the apparatus that is writing. So they use this idea for real devices, storage devices. And this is nanoscale. What is going on larger scale? Can we control friction at larger scale, applying tiny oscillations? And we studied the system which actually mimics earthquakes. This is large scale. As I told you, you have friction between tectonic plates. And usually what you have in nature, okay, system is stuck. It starts to move. This is earthquakes. And each of all these systems, they're erratic. You cannot predict time intervals between earthquakes. Now, this is you have very broad distribution of times between earthquakes, and because of this, it's very difficult to predict them. So we tried to apply tiny oscillations to this system. And what is happening? No, we cannot reduce friction. But we can, you see, as you can see here, we can synchronize this effect. So we had very broad distribution of times between earthquakes. Now applying very tiny vibrations. Actually, you can synchronize them, and I hope probably, and now people are, this is experiments, of course, laboratory experiments. Now people are doing field experiments, and you know, we will not be able to eliminate earthquakes, but maybe we will be able to make them predictable. Okay? So, and the last point on which we are working, another way to control friction. Control friction applying electric field. For instance, these are results of experiments and simulations in electrochemical system, where you have two electrodes, you apply electric field between these two electrodes, and you change your properties of the interface. As you can see here, this is very simple system, just pyridine organic molecules. I see here organic people sleeping. Okay, but these are organic molecules. Okay, so you can change orientation of these organic molecules. You can change frictions order of magnitude. So we are working on this. And another work which we are doing in my group, we are using now ionic liquids, which became very, very popular during the last few years. And again, this is liquid completely built from ions. Again, applying field between two electrodes. In this case, it has been shown already experimentally at our first works and also in simulations. We can find conditions where you can change friction more than order of magnitudes. Okay, I will stop you at this point and thank you for your attention.
Quick question? Yes, please.
One short question. Is it possible to, in a few words, to explain what happens in the macro when you actually can bring the release into a certain time interval?
Okay, yes. Because on macro scale, actually, there are different kind of fronts propagating across the interface. Okay, and actually, you all this work. I think I'm okay. Yeah. For you, yeah. Okay. So, as I told, on macro scale, there are different kind of fronts propagating a lot of interface, and applying this tiny oscillate. And actually, your system is always at the threshold of rupture. Applying very tiny, you are already very close to threshold. You apply very tiny oscillations, and you eliminate part of the fronts, and in this way you make this predictable. This is the mechanism. And this is possible only because in this earthquake system, you are already very close to the threshold.
What's the mechanism here for the ionic liquids?
For ionic liquids. Okay, the mechanism is very simple. What is these ionic liquids? It's two ions. Let's imagine just simplest ionic system which we know. Okay, sodium chloride. Sodium and chloride, what's the difference? One positive, one negatively charged, and they have different size. Change in electric field, in one case, sodium atoms near the interface, sodium ions near the interface, you change electric field, chlorine ions near the interface. Interaction between surface of the substrate and sodium and chlorine is different. So changing electric field, you can change friction. You can change properties of your interface.
Yes.
Can you comment, I mean, at the nano scale of the relationship, not between the structural features of the surfaces, but rather the chemical ones, in a way, and deal at the level of type of forces, I mean, between those entities?
You're asking me what kind of forces we have at nanoscale?
Well, at nanoscale, but also correlating it with the structure, the types of chemistry. Let's say if you take two plastic surfaces, but you cover them with different functional groups.
Of course, this will influence dramatically.
Apart from charges, I mean,
You know, as you know, there are different kind of interactions in the interface. Electrostatic interaction, van der Waals, chemical interactions. Usually, let's say, in these systems which have practical applications, usually have kind of chemical interaction. So because of this, usually you have high friction, yeah. But in this case, actually, we play, still there are not only electrostatic interactions, but we are playing with electric fields, changing, okay, just, you know, changing interaction between systems, bringing different kind of ions to the surface.
Now I understand that what Michael really wants is not a world without the friction. It's a world with a switch.
With desirable friction, I will say.
Right. On and with friction.
Yes.
Off without friction.
So next time we'll go for hiking, I will switch on friction.
All right. Very
Okay?
good. Okay, let's thank Michael.